Hey everyone, and welcome back. This explainer is brought to you by Forge College. Today we've got a really fantastic, highly practical goal, comparing cost scenarios and preparing to optimize. We're going to take all those raw gas numbers we've been crunching and synthesize them so we can actually prep our smart contracts for optimization. We are turning pure data into a solid, actionable engineering plan.
Now I know what some of you are probably thinking. Wait a second. Weren't we just up in the breezy, high-speed clouds configuring Solana cloud settings in our last lesson? Well, yes, we absolutely were. But grab your hard hats and your flashlights because today we're dropping straight out of those breezy clouds and down into the dank Ethereum basement. It's time to check our smart contract plumbing. Watch out for the cobwebs down here.
Here is our engineering blueprint for this session. 1. A welcome to gas optimization. 2. We'll look at the pipes in the thermostat. 3. Comparing cost scenarios. 4. Your 5-step workflow. 5. Writing your synthesis note. And 6. Next steps and wrap up.
Let's dive right into Section 1. Welcome to gas optimization, moving from data to action.
So we're officially shifting from just producing raw data to interpreting what it actually means for our users' wallets. What do we mean by gas optimization? It's all about identifying and targeting the highest impact cost levers in a contract, rather than chasing marginal, low-value gains. A good optimization strategy means prioritizing your effort exactly where it saves the absolute most money. You really don't want to spend 40 hours of dev time to shave off 2 gas units on a background function that literally no one ever calls, right?
Which brings us to Section 2, pipes and the thermostat. This is our core mental model for the day.
Whenever you're thinking about Ethereum transaction costs, I want you to picture a standard household water bill. It's a brilliant way to break this down into 2 distinct parts. On the left side, you've got the pipes. This is your flow reduction. The pipes represent the actual volume of your transaction, your gas used, your opcodes, your storage operations, your call data. You have total control over replumbing your code to shrink these pipes. But on the right side, we have the thermostat. This is variability reduction. This represents the dynamic network pricing, things like the EIP 1559 base fee, priority fees, and the timing of your transaction. You can't control the network's thermostat. You can only adapt your contract's sensitivity to handle it.
Now, before we look at the real numbers, we have to establish our safety mantra for the day. Say it with me. Normalize your units. Seriously, you always need to convert GUI to ETH, or at least use a standardized metric before comparing scenarios. If you don't normalize, you'll be comparing apples to oranges, and your optimization targets will end up completely backwards.
All right, moving to Section 3, comparing cost scenarios. Let's see this math in action.
Let's look at how a rising thermostat drastically changes the underlying math across 3 distinct scenarios. We'll assume a baseline transaction of 150,000 gas. In scenario A, network congestion is super low. We've got a base fee of 20 GUI and a 1 GUI tip. So our total cost is a very reasonable 0.00315 ETH. But check out scenario B. It's the exact same 150,000 gas transaction, same exact code, but the network is congested. The base fee spikes to 200 GUI, the priority fee jumps to 50 GUI, and suddenly our total cost skyrockets to 0.0375 ETH. The thermostat went up and our bill just exploded. Finally, scenario C. Here, we actually went in and changed the plumbing. We optimized the code, maybe cut down on storage rights, and brought our gas usage down to 110,000. Even during that exact same peak congestion from scenario B, our new cost drops down to 0.0275 ETH.
When we visualize that, the impact is just undeniable. Look at that massive 10x visual jump between scenario A and scenario B. That right there is pure thermostat volatility. But by shrinking the pipes in scenario C, specifically by reducing expensive stuff like storage and call data, we save roughly 26% compared to scenario B, even under peak network stress.
So, the absolutely crucial takeaway is this. An optimization that reduces gas used by just 5%, but successfully reduces your variance and sensitivity to base fee spikes, can actually be worth way more financially than a massive 20% one-time gas reduction that still leaves you completely exposed to peak congestion. Sometimes, building a shock absorber for the thermostat is way better than just shrinking the pipe.
Next up, Section 4, your 5-step workflow, going from math to action. Here's a really crisp, repeatable action plan you can use every single time you analyze a contract. Step 1, collect and normalize your data, like we just talked about. Step 2, break down the cost contributions. Figure out exactly what percentage of the bill is storage versus call data. Step 3, rank those drivers. Step 4,
estimate the implementation cost and risk for your dev team. And step 5, create your synthesis note. This workflow takes you straight from raw calculator outputs right to a prioritized engineering plan.
Let's zoom in on step 3 for a second, because this is kind of the secret sauce. You want to use a 2-axis ranking. You're evaluating cost drivers by absolute impact, meaning the potential raw savings, and by volatility, meaning how much that cost shifts when the network gets congested. Drivers that are high impact and high volatility, those are your prime candidates for big structural architectural changes. But drivers that are high impact and low volatility, those are usually your low-risk, quick-win plumbing fixes.
But hold on, before you touch a single line of code, you have to pass this checkpoint. Ask yourself, does this proposed optimization actually have a payback period of under 12 months? You've got to weigh the projected monthly ETH savings against the cost of developer hours. Please, whatever you do, don't chase technically fascinating, mathematically beautiful micro-optimizations if they are financially useless. If it takes 80 hours of expensive dev time to save $3 a month in gas, put the keyboard down, step away from the IDE, and rethink the plan.
Okay, section 5, writing your synthesis note to formalize these findings.
Assuming you've found a worthwhile target, it's time to formalize it into a concrete deliverable. Here is the anatomy of a perfect synthesis note, which should be entirely focused on actionable, evidence-based recommendations. First, keep it under 300 words. Nobody wants to read a novel. Next, clearly list your top 3 cost drivers. Then, detail 2 concrete optimization targets. Estimate the direction of the savings. Is it a percentage drop or absolute ETH saved? And finally, always attach your normalized scenario table as your hard evidence.
So what does a good target actually look like? Something exactly like this. Batched call data for N operations, yielding a 12% absolute cost reduction during peak hours. Notice how specific that is? It maps perfectly back to our plumbing and thermostat analogy. It tells us exactly what pipe we're adjusting and exactly how it's going to perform when the thermostat gets cranked up.
And that brings us to section 6, next steps and wrap-up.
We have covered a ton of ground today, so I want to leave you with one final provocative question. What will you optimize first? Are you going to go after those heavy storage pipes, or are you going to build a shield against network volatility? Remember to synthesize your data. Write up your notes and bring it with you to our next session, where we'll start applying these principles directly to your specific targets. As a reminder, this explainer was brought to you by Forge College. I highly encourage you to head over to forge.college to learn more about this subject, access our tools, and explore a ton of other fantastic Web3 topics. Thanks so much for learning with me today, and I'll catch you in the next one.